Hello once again, class, and welcome to another mock lecture. In today's video, we are going to talk about continuity. Now, you might know continuity from pre-calculus, right? In pre-calculus, we have this really kind of vague definition that's more like the concept image behind what's going on, but it says that if you can graph a function without lifting your pencil, then it's continuous. And that worked, right, for pre-calculus stuff. But now that we're armed with the knowledge of limits, we're ready to define this thing more rigorously. So the definition goes like this. A function f is continuous at a point A if and only if the following three conditions are true. The first one says that f of a is defined, meaning a is in the domain of f. The second one says that the limit as x approaches a of f of x exists, meaning the left-hand limit and the right-hand limit at a agree with each other. But crucially, the limit as x approaches a of f of x has to be the same value as f of a. That's what makes a function continuous. Right? You can see from this particular graph, which just visually is not continuous, it's really that last condition that pulls everything together and makes graphs continuous, right? If they satisfy these three things. Case in point, this graph here has f of a defined. Right here it is. It has that the limit as x approaches a of f of x exists. The left-hand side limit and the right-hand side limit both go to whatever this particular value is, but it doesn't have that the limit as x approaches a of f of x is the same, right, as f of a. And so this particular graph is not continuous. And there's really three main types of discontinuity that we're going to talk about. The first is this graph here, right? That's called a removable discontinuity. It's like you picked a point out of the graph and you just moved it somewhere else. That's removable discontinuity. You can have a jump discontinuity, right? You'd see these things all the time in like a piecewise sort of function. And then you can have an infinite or an asymptotic discontinuity, which happens all the time with rational type functions. The tangent function is another one that has infinitely many, right, vertical asymptotes. And although they're discontinuous on a specific interval, maybe this particular graph is discontinuous on the interval x1 to x2, but we wouldn't say that it's discontinuous on its apparent domain, and more on that in a little bit. But first, we're going to consider the following three super similar functions. You might notice that they're all, in some part, defined by the p of x function, which is x squared minus 4 divided by x minus 2. And what I want to do is I want to figure out which of these are continuous at the point x is equal to 2. Well, we have to satisfy, right, the three main conditions for continuity for them to be continuous at 2. The first is that f of 2 exists, which is true for all of them except the function p. You cannot plug 2 into p, the denominator becomes 0, and so you have something that's undefined. But the other two pass. The second one says that the limit as x approaches 2 of f of x has to exist, and we basically get that by way of direct substitution. We can simplify this thing. This thing becomes the limit as x approaches 2 of x squared minus 4 divided by x minus 2. Well, this thing factors into x minus 2 and x plus 2, and so you get to cancel the common factor in the numerator and the denominator, and then now we're allowed to use direct substitution on this, because 2 is certainly in the domain of this function. But the last one says that we have to have the limit as x approaches 2 of f of x equal to f of 2, and that eliminates h, right? At 2, f of 2 is 3, okay? But q of x is actually fine. Even though it's in part defined by this function that does not have 2 in its domain, we're defining q of x to not care what's happening at 2 for the part that's problematic. Instead, this thing is just discretely defined as, well, it's 4 when x is equal to 2, and so this is true, meaning that q of x is actually the only continuous function at the point 2 that's listed on this page. So cool. Right, we get how continuity at a point works, almost, right? How would we define continuity at an endpoint, right? Endpoints are points, and right now, if we have to have that condition where the limit as x approaches a of the point, right, of f of x to exist, a is an endpoint, and so based on this graph, we can't say something like the limit as x approaches a of f of x exists at all, because the right-hand limit, while it exists, can't agree with the left-hand limit. There is no left side of this endpoint. So instead, we're going to actually have to define endpoints slightly differently by using one-sided limits. So I put on here, currently we can find that f is continuous at every point on the open interval a to b, but we cannot show continuity right now based on what we have for the closed interval a to b for the exact reason that I just said. There's not a double-sided limit to look at for these two endpoints. So what can we do? Well, we just define it one-sidedly, right? So a function is continuous from the right at a point a if the limit as x approaches a from the right of f of x is equal to f of a, and we can say a similar statement for approaching from the left, right? So it's continuous at a point from the left if this limit, right, is true, right? We're approaching from the left in this case. With this, we get continuity on a closed interval. And in general, a function f is continuous on a closed interval, provided that first it's continuous on its open interval. So it's continuous on every point inside the open interval a to b. And then the two one-sided limits are also true. And if we can show that, then we get that the whole thing is going to be continuous on the closed interval, right? This gives us the open interval. This gives us the endpoints. So now we get the closed interval. We can say it's continuous on that. All right, up next, we've got the continuity of some combination functions, and this is pretty cool. If f and g are both continuous at a and c is a constant, then the following are also continuous at a. And in this video, we're not going to prove this stuff. The proof of this mostly comes from the limit laws. I'll actually show you one of them. Here it is. Feel free to pause this and look at it in all of its glory. But you can do that basically for every single one of these things. So you can prove them. They are actually pretty straightforward. And maybe we'll do some in class or something like that. The other cool thing is that composition also works. So we can define composite functions being continuous at specific points as well. So if f is continuous at, let's say, the point L, and the limit as x approaches a of g of x is equal to L, then the limit as x approaches a of the composite function f composed with g of x, we can just say, and by the way, this is the definition, right, of a composite function. F composed with g of x is just defined to be f of g of x. But what you're allowed to do is you're allowed to basically bring the limit inside of the f function. So now you're taking f of a limit, and we already know that that's L, so it's just f of L. So I kind of paraphrase this, and this is how I think about it. In other words, if g is continuous at a and f is continuous at g of a, then the composite function f composed with g is also going to be continuous at a. Function composition is that thing where you're plugging one function into another function. And so if we're starting with a and we're saying, oh, hey, this is continuous at a, and then f is continuous, right, at g of a, then f is continuous at a. That's the way that that works. Okay, now this, together with the other combinations functions continuity theorems, is pretty cool, right? It's objectively awesome. But do we even know that many continuous functions? As it turns out, yes. In fact, literally every function that you've talked about prior to this class is continuous. There's a catch. It's continuous on its domain. So you can't just pick an interval and say all of these things are continuous on it. Radical functions, for example, are not defined to the left of the x-axis. But these are all functions that you've seen before. And actually, I'm just realizing I didn't put on power functions. Radical functions are basically a specialized power function. But power functions work too. For example, x to the 1.3, right? That would be continuous on its domain as well. But I listed all the domains here. Again, feel free to pause this if you wanted to take some notes on what these specific domains are. I also didn't include stuff like the reciprocal functions, the reciprocal trig functions like cosecant, secant, and cotangent, but those also still apply. They'd be continuous on their domains. The evidence for this, by the way, because I'm not going to prove this to you guys. In fact, we might, during the duration of this class, I may have you guys show that these functions specifically are continuous. They're actually not super hard to do. You essentially just get to use some definitions of continuity on them. But the evidence for why this is the case would be just to look at their graphs. And I think that if you look at a rational function and you might be like, wait a minute, Mock, there's an infinite discontinuity there. That's true, but whatever that value is, it's not in its domain. Right, so all these points on the left and the right, they approach this vertical asymptote, and you could show that they satisfy continuity at a point. All right, so everything that's in the domain of these functions, that's kind of the takeaway here. If you want to find where a function built from these is continuous, you're just going to find that function's domain. So I just threw a ton of information at you. Let's take a look at a few examples. All right, example number 1. We're going to show that k of x, which is equal to the square root of 25 minus x squared, is continuous on the closed interval -5 to 5. Okay, now I'm going to show you how straightforward this kind of proof is. Remember, there's 3 conditions that we have to prove are true for something to be continuous on a closed interval. Number 1, you have to show that it's continuous on an open interval. Number 2, you have to show that the right-hand limit of its left endpoint is equal to k evaluated at that left endpoint. And then also that the left-hand limit, oh no, I made a mistake here. That should be a left, that's from the left. The left-hand limit of its right endpoint also exhibits the same behavior. And just as a warning, that's going to switch back to a plus when I change the slide here, but just pretend in your mind that it's a minus sign. So we're going to go ahead and we're going to let C be some arbitrary point in the open interval -5 to 5, meaning that this is the case. C is between -5 and 5. Pick whatever you want, right? It's arbitrary. But I'm going to show you that the function is continuous at C. We know that the limit as x approaches c of the square root of 25 minus x squared is just equal to, by direct substitution, the square root of 25 minus c squared, but that's just f of c. That's the definition of f of c. So, okay, k of x is continuous on -5 to 5. The next thing we have to do is we have to show that the left-hand limit of the right endpoint and the right-hand limit of the left endpoint also exist, and they do, also kind of via direct substitution. Right, so we've just immediately satisfied all 3 of these conditions, and so we know that k of x is indeed continuous on -5 to 5. Now, another thing that's interesting is that that closed interval is in fact the domain, right? Remember we were talking about if you want to find where a function is continuous, right? That's built from all these pre-calc functions, all you need to do is find its domain. So I could have actually skipped all of this stuff, and I could have just found the domain of this thing instead, which would have been when 25 minus x squared is greater than or equal to 0. As there's a polynomial inequality, we would get the same thing, right? We'd get the closed interval -5 to 5. Number 2, find the interval or intervals for which L of x, which is this kind of weird looking, not really rational function since the numerator is not a polynomial, but it's some kind of combination function that involves logarithms, exponential functions, and a quadratic. Show the intervals for which this thing is continuous on. Well, that basically just means find its domain. And again, if you want to find where some pre-calc combination function stuff is continuous, all you need to do is figure out what the collective domain is. For combination functions, basically I just look for the most restricted function, and I start there for my domain. The most restricted function here, as far as what you can plug into it, is definitely the natural logarithm. It's got a domain of 0 to infinity. You cannot even plug 0 into any logarithm, nor can you plug negative stuff into it. So, okay, we're starting here. Is there anything else that would further restrict the domain? Well, there is a denominator, and so that can never be 0. Let's figure out when that's equal to 0 by solving this equation, and we get that x can't be equal to plus or minus 1. Well, since the domain that we're starting with is actually only positive numbers, I just did away with the -1. I just got that out of there because that's not even in this thing. And so the domain overall is going to be 0 to infinity, and we're going to exclude 1. I chose to write it as 2 different intervals with a union sign between them. So it's the interval 0 to 1, union 1 to infinity. So L of x is continuous on that particular domain as well. All right, now let's do a composition function, right? These are a little bit more interesting. But again, if you want to find where a function is continuous, just find its domain. So we just need to find the domain of this thing. Sine squared of x is the very first function that's used. I always like to say x begins its journey, right, with sine squared of x. Composition functions is that thing where, you have kind of 3 different sets. You're starting in the domain, in this case, of sine of x, and then that maps you somewhere to the range of sine of x, which, by the way, the range of sine of x is really small comparatively, right, to its domain. Then, hopefully, wherever you land, is inside the domain of the outer function, in this case a logarithm, whose domain is actually 0 to infinity. And if it is, then you're allowed to run it through the next function, right, to figure out what's going on. So I'm going to say this is sine squared of x, and then this is the log of the sine squared of x. That's what happens when you run an x value through a composite function like this. So we don't want to get 0. We know that whatever we plug into the sine squared of x, we're always going to get back something that's between 0 and 1. And by the way, you should try to figure out why that's the case. I don't think I'm going to explain it here, but it should be, you do want to know why is the range of sine squared of x 0 to 1, right? The closed interval 0 to 1. In any case, 0 is not good, so we want to make sure that sine squared of x is not 0. Whatever those x values are, we're going to exclude it from this domain. So right now we're looking at, here's where x starts from here. Turns out it's always positive. So actually, even though this is a logarithm, we're going to get to plug some stuff into it that's negative because it first gets run through sine and will become positive, or 0, right? Could be 0 too, and that's what we're trying to avoid here. So to figure out what we should avoid, let's solve this equation. Sine squared of x is equal to 0. Well, first I'll go ahead and square root both sides, right? Just going to give me sine of x is equal to 0. And then I'll take the arc sine of both sides to get to cancel the sine. When you plug a function into its inverse, they undo each other and you just get x. In this case, we're getting a reference angle. The reference angle that we get is 0, and that reference angle can also happen at pi. Sine of x is also going to be 0 at pi. So that means that if the reference angle is 0 and also pi, everything that's 2 pi away from either of those values is going to be bad news for the domain. For example, you can't plug in negative 15 pi to this thing because that would make sine x 0. You square 0, you still get 0, and then now you're plugging 0 into a logarithm, which is not good. You can't do that. So any whole number, that's not true, any integer number amount of pi is off limits, right, for the domain of this thing. So a way to consolidate this is to say, well, x can't really be equal to pi n, where n is an integer, and that's our domain, right? So here it is. I wrote it in set builder notation this time instead of an interval because there'd be infinitely many intervals. Basically, x is all real numbers such that it's not some kind of positive or negative multiple of pi. And since that's the domain, that's where s of x is going to be continuous. All right, now there's one more thing I wanted to touch on in this video, and it's actually really important for continuous functions. Really important to know for continuous functions. It's called the intermediate value theorem. What it says is, let's suppose that f is a continuous function on the closed interval a to b, and there's some z value that's between f of a and f of b. So z is some value that's between the output of a and the output of b, and it's definitely between them because we're saying that f of a is not the same as f of b. They're two different outputs. If that's true, then there exists a c value inside this domain that we're considering, inside the closed interval a to b, such that if you evaluate f at this c, you get z. So let me try to explain this pictorially. Right, here's kind of what's happening. So we've got this function, and in this thing, it's continuous seems to be further beyond a to b. But let's say that we only care about what's going on from a to b. Okay, and it is objectively continuous. Just look at it. It's continuous on the closed interval a to b. Well, it also has f of a values and f of b values. Right, that's just the way the functions work. So a gives you f of a, and b gives you f of b. Okay, this thing is saying, and at this point we've satisfied everything that there is to satisfy here, except for this. Z is somewhere between f of a and f of b. Okay, now we've satisfied all the preamble, right, stuff for this theorem. The conclusion then is there exists some c that's inside this interval. So a c between here that when you plug it into f, you get z, and there is. Right here it is in this particular example. Okay, now you might be saying, well, okay, that's just, you drew this like that, so of course you're going to find a solution, but pick a z value. I bet you picked it right here. Okay, well then the c value that gives you that z value, I would say, is right here. Right, if you evaluate this function at c, it appears that it gets you a height of z. Okay, that's how it works. You can pick any z anywhere. You're always going to be able to find a c that when you evaluate the function at that c gives you that output. Now, you might also be saying, oh, well, this is a graph, right? Of course, we're going to be able to find something that gives us any particular z value between these two things. It's a continuous graph. Of course, we can do that. Well, let's say we don't have a graph, right? And this is really why the intermediate value theorem is so important. It can help us find roots of particular functions. In this case, I want to show that t of x, which is some cubic function that's rising to the left and falling to the right, and I know that because of its negative leading coefficient and the fact that it's an odd degree. That's just how end behavior works for polynomials. So I know it's got a root somewhere, but I want to show that it has a root, a 0 is what I'm calling it here, on the closed interval 1 to 2. So again, like my picture of this thing in my head looks like this. I just don't know where the root is, but I know that it's coming up from the left, right? And then it's going down towards the right, again, just because of end behavior stuff. So what I did is I evaluated the function t at 1 and at 2 because we need some y values, right? Z, in this case, is actually 0. We're trying to figure out that this thing has a 0, so we want to know that, well, is 0 between the two, is there a 0, right? That's between the two outputs that are defined by the x coordinates of our interval here. Okay, so I first got those values. We also know that t of x is continuous on negative infinity to infinity. It's a polynomial. Now, I didn't need to write this. I could have just said this, because that's the interval. That's the only interval that we care about here. But it is continuous on negative infinity to infinity. And so finally, notice that 0, right, the value that we want to get is indeed between 2 and negative 5, right? It's between t of 1 and t of 2. So we just get for free by the intermediate value theorem that there exists some c value. We don't get to know what it is, but it's a c value that's between 1 and 2 such that t of c is 0. So there exists a 0, right, for this thing. If you wanted to zero in, that's a good pun. But if you wanted to maybe hone in, is a better verb here, on where that 0 might exist, you could just try changing these boundaries, right? The same process is going to happen. I think, don't quote me on this because I actually didn't check, but I think that the 0 happens around the x value 1.32. So if you were going to check here, hopefully this evaluated through the function t of 1.31 is something that's positive, and then the t of 1.33 is something that's negative, and 0 would be between whatever those things are. So the intermediate value theorem would say, hey, there's a 0 between even these two things. But that requires a little bit of guesswork, and this is more just sort of like, hey, we can prove that there exists an x-intercept somewhere. We don't exactly know where it is, but we know it's between 1 and 2. And that is one very important application of the intermediate value theorem. All right, so that's it. Hopefully you guys learned something. If you have any questions, please shoot me an email or drop a comment below. Thanks a ton for watching, and I'll see you in the next one.